The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. Right, so eventually today we're going to go on to section 9.2. But first, I have a couple of questions that were requested through email, and then I'll see if you have any questions of your own. So this is in section 9.1, part 2, number 11. It says, simplify the radical expression. Assume the variable is unrestricted. And we are to take the 6th root of 64b to the 6th power. Well, if we take 64 and we break it down into its prime factors, we get 2 to the 6th power. So if we have the 6th root of 2 to the 6th power times b to the 6th power, well, the 6th root of 2 to the 6th is 2. And the 6th root of b to the 6th is b. Now, this is the answer that the student that asked wrote, but what's wrong with it? Well, here's the deal, okay? Again, the directions said, simplify the radical expression, assume the variable is unrestricted. That means that b could be positive or 0 or negative. Well, let's go back and review some rules. You can't take an even root of a negative number and get a real answer. Also, when you take an even root of a number, you can't get a negative answer. So if b is unrestricted, that means b might be positive or negative or 0. But since I've got b as part of the answer here, I have to make sure it's not negative. So the way to do that is to put absolute value bars around the b. So there is the correct answer, 2 times the absolute value of b. That way, if b is negative, we're still assured that 2b is a positive or at least non-negative answer. Any questions about that before we go on to another example? All right, this is also 9.1, part 2, and this is number 14. It says, use a calculator to solve the problem. All right, the time t in seconds that it takes for an object to fall a distance of s feet is given by the formula t equals the square root of s all over 4. The time t in seconds it takes for an object to fall a distance of s feet is given by the formula t equals the square root of s over 4. In some places, the Grand Canyon is 1 mile, that is 5,280 feet deep. How long will it take a stone dropped over the edge of the canyon to hit bottom? Round your answer to 1 decimal place. Okay, let's see here. Let me read this statement one more time. The time t in seconds that it takes for an object to fall a distance of s feet. So s is in feet, and we're looking at 1 mile or 5,280 feet. So t equals the square root of 5,280, all of that divided by 4. So on the calculator, I'm going to put in second and then square root of 5,280, close that up. So I've got 5,280, close that up, okay? And then all of that divided by 4. And I get 18.16590212. It's important that you close that off, because if you don't, if you just leave it like this, the calculator might think that this whole thing, oops, that this whole thing is inside of the radical. So you need to be sure and close up the radical before you divide it by 4. All right, it said what did it say? Round to 1 decimal place. So we go to the first decimal place. We go 1 further over, the 6 rounds up, so 18.2 seconds would be the final answer. Any questions about that problem? All right. Any questions about anything else before we go on to section 9.2? Anybody?
Can you do number 16?
Number 16. Okay. Let me find your number 16. Let's see here. There we go. Number 16. So again, from 9.1 part 2. Yes. Okay. All right. This one, I'm actually going to show the graph because I think it'll help with the problem rather than having to redraw the whole thing. So use a calculator to solve the problem, it says. The graphs of 2 radical functions shown in the illustration can be used to estimate the speed in miles per hour of a car involved in an accident. Suppose the police accident report lists skid marks that are 240 feet long, but failed to give the road conditions. Estimate the possible speeds the car was traveling prior to the brakes being applied. Round your answer to the nearest whole number. Interesting. I don't see a formula given. Do you? So
there's no formula. I think you just have to look up the graph and see.
Yeah, and the reason I'm baffled is that it's like it says use a calculator to solve the problem. So if there was a formula, apparently they missed giving it to us. All right, well, we'll play it by ear here. Okay, estimate the possible speeds the car was traveling prior to the brakes being applied. So let's see here. Length of the skid marks, 240 feet, all right? So down here at the bottom, each one of these little increments is what? 1/5 or so, 20 feet. So 240 feet would be right there, okay? So it looks to me like that first one, drive pavement. I wish I could zoom in on this and make it bigger, but if there's a way I don't, well, let's see what happens if I do this. That doesn't make it any bigger anyway. Anyway, so 240 right there. It looks like it's slightly above 75. So my first guess, I think, would be 76. That would prove to be wrong. And then I'd try 77. And again, I feel like there's something missing from this problem, some formula or something, but I'd say a best guesstimate would be 76 or 77. And the correct answer, as you can see, is 77. Don't panic if there's something like this on the test. I will take that into consideration. All right, wet pavement is going to be right there. Again, I would guess 50, as did the person that asked about it. They're saying 49. So my guess is that there's some formula that we don't have given here that we're supposed to have, okay? Anyway, don't panic about that. There's your answers. Dry pavement, 77 miles per hour. Wet pavement, 49 miles per hour. Okay, anything else?
Question number 2, please.
Question number 2, okay. Let's see here. Who asked for that one?
Juliana.
Okay.
I sent over an email. I must have sent it late though.
Yeah, I checked those. It has to be like before 10 o'clock. And maybe you did send it before 10 o'clock. I don't know. Anyway, not a problem. Not a problem. Okay, let's figure out which. There we go. All right, also from 9.1 part 2.
Yes.
And I'm assuming you want number 2, 14. Let's see, 2 and 14.
Yes, those two, please.
Okay. So number 2 says, use a calculator to find each function value, round to the nearest 10,000th. So we have g of x equals the square root of 7 minus 4x. And then part A is g of negative pi. And part B is g of 0.5. Okay, so back on the whiteboard screen, g of negative pi would be the square root of 7 minus 4 times negative pi, which is the square root of 7 plus 4 pi. Okay, the square root of that. So on my calculator, I'm going to put in second square root. So I've got this, then 7 plus 4. Now, the pi button, let's see here, put on my glasses. On this calculator, I know it's on here. Pi. Well, that's interesting. Pi. Let's see if I can find pi on here. Oh, here it is. Duh. I was looking for a second function key, and it's a first function key. It's right. It's on this column right here. It's right there. It's a pi button. Okay. So I push that. And then close it up with right-hand parentheses equals. And I get 4.423389042, but it says round to the nearest 10,000. So this is 10th, 100th, 1000th, 10,000th. We go one place to the right, the 8 rounds up, so 4.4234. I'll write that over here, 4.4234. All right with that? Okay, next one. Square root of 7 minus 4 times 0.5, which is the square root of 7 minus 2, or the square root of 5. So then second square root of 5. And I get 2.236067978. Rounding to the nearest 10,000th would be there. The 6 would round up. So 2.2361 would be the second answer. Okay with that?
Yes, thank you.
And then number 14. All right, this is similar to the one. Actually, it's the exact same number 14 that I did a little bit ago. Okay. Just want me to go over that again?
No, that's fine. Thank you.
Yeah, it's the exact same number. Sometimes they're the same numbers for different students, sometimes they're not. Okay, any other questions, anybody? All right, then we're going to go on to section 9.2, as I mentioned. And let's see here. Close that up. And I should be at the whiteboard screen. All right. So not this quarter, but in a previous quarter, in either Math 84 or Math 85, or perhaps a beginning algebra class in high school, you should have at some point covered properties or rules or shortcuts involving exponents. We're going to be reviewing those today and using them in a new way. I just want to point out, hang on, I wrote this down and then I threw it away. So in the regular textbook on page 364, which is section, so page 364, section 5.2, it lists all of these properties or rules that we're going to be using today. So if you want a reference point, now I don't know as far as the online ebook where it is, but it's in section 5.2 towards the end of the section. Okay, so I'm going to be reviewing those and then applying them in new ways today. One of the rules says, if you are multiplying two powers with the same base, you add the exponent. So a to the m times a to the n equals a to the m plus, plus n. So for example, x to the fourth times x to the third would be x to the seventh power. Y to the 10th times y to the fourth would be y to the 14th power. Any questions about that rule? Okay, so there's one of them. Another rule says, if you're dividing two powers with the same base, you subtract the bottom exponent from the top exponent. So a to the m divided by a to the n is a to the m minus n. And this is all in the numerator, so it's like it's over 1 if you need to know in terms of its location. And that looks like a u, it's supposed to be an n. So for example, x to the 5th divided by x squared would be x to the 5 minus 2 power, or x to the 3rd power. Y to the 15th power divided by y to the 3rd power would be y to the 15 minus 3, or y to the 12th power. So there's a second rule. Any questions about that? Okay. Another rule, if we have a power, let's see, power raised to a power, you multiply the exponent. So let's say x cubed to the 4th power would be x to the 12th power. Y squared to the 8th power would be y to the 16th power. So again, a power raised to a power, you multiply the exponent. Careful you don't get these two mixed up. Another rule, if we have a, let's see, a product raised to a power, we attach that outside power to each factor of the product. So for instance, let's say I have 2x, the quantity cubed, that's 2 cubed x cubed. Or simplifying further, 8x cubed. So there's yet another rule. And let's see, we'll start with those and then we'll add more as we go. All right, so here is an example. This says, evaluate each expression. And we'll get to using those rules here in a minute. I overlooked this first part, but let's see. If we have, hang on a second, I want to jump it in with something. And yes. Okay. Let's say we have the cube root of 8. So this is radical notation. And I want to write that in exponential notation. The index becomes the denominator of the exponent. So the cube root of 8 is equal to 8 to the 1/3 power, or in general, the nth root of a equals a to the 1/n power. Think of it this way. If this was a tree, the roots would be on the bottom. This is the root, right? Cube root. So the 3 becomes a 3 in the denominator. So the cube root of 8 is 8 to the 1/3 power. Okay. Or 125 to the 1/3 power would be the cube root of 125. Now, we already talked about the xth root yesterday. So for instance, we could put this into our calculator using that. And so we'd start out with the 3, the index, and then second x root and then 125, and you should get 5. But let's put it in this way, all right? Get on the calculator. On that left column, there is a little, what we call the caret key, which is a power key. It's actually it's the button that you push and then do that's the second function gives you this. So the first function is that, the second function is that, okay? I'm going to take 125 to the 1/3 power. So I put in 125, then use that little caret, parentheses, 1 divided by 3, close parentheses, and that should give me a 5. If you have a graphing, if you have a scientific calculator handy, I would suggest you try that right now. And if it's not working, let me know. Otherwise, you can deal with it later. Okay, so let's say we've got this situation. We've got 625 to the 1/4 power. So on the calculator, I could put in 625, little caret key, 1 divided by 4, close it up. Okay, 625, caret key, 1 divided by 4, close it up, and I get 5. You could also do it by hand and say, well, this is the same thing as that, and 625, you could break it down, and eventually you'd get there. So you'd have the 4th root of 5 to the 4th, which is just 5. Notice how the index and the exponent reduce out, cancel out, whatever you want to call it. So you end up with 5. Any questions about that? All right, now let's get into these rules that I jumped into the first part and should have waited on. Okay, let's say I've got this. I've got 4x to the 4th, all to the 1/2 power. So simplify each expression, assume that the variables can be any real number, and use absolute value symbols when necessary. Now, earlier the direction said assume the variables are unrestricted. Now they're using this language, assume it can be any real number. Same thing, okay? So I've got a product raised to a power, which would be this rule right here. So this is going to be 4 to the 1/2 power, x to the 4th to the 1/2 power, okay? Which is 4 to the 1/2 power, x to the power raised to a power, multiply the exponents. 4 times 1/2 is 2. So what I've got now, let me make this a little more legible, is 4 to the 1/2 power times x squared. Well, 4 to the 1/2 power, that's like the square root of 4, which is 2. So I get 2x squared. Now, I know 4 times 1/2 is 2, but I didn't multiply it by 1/2. I raised it to the 1/2 power, or took the square root of it. Do I need absolute value bars here? No, I don't, because even though x could be negative, since it's squared, even a negative times a negative would be a positive. So that's my final answer. All right, how about this example? X squared to the 1/2 power. Well, that would be x to the, let's see, a power raised to a power, multiply the exponents. 2 times 1/2 would be 2 over 2, or 1. So the answer is x. But that's not the final answer, because we're taking an even root. So our answer can't be negative. And since the direction said that x could be any real number, in this case, I need absolute value bars on the final answer. What about this one? X cubed to the 1/3 power. Well, this is also x, but because I'm taking an odd root, I can have a negative answer. So again, the restrictions are on the even roots. You can't take an even root of a negative number. When you do take an even root of a number, you can't get a negative answer. So you've got that connection. Even roots can't have a negative inside, can't have a negative outside. So if you're, so let's do it this way. Even root, if this is negative or that's negative, you're in trouble. Okay. How about this one? Negative 16 q to the 4th to the 1/2 power. So this would be negative 16 to the 1/2 power, q to the 4th to the 1/2 power, negative 16 to the 1/2 power, q to the what, second power. But I could have stopped a long time ago because look right here, I'm taking an even root of a negative number, so it's not real. Okay. 243 x to the 10th all to the 1/5 power. Okay, let's see here. So we've got 243 to the 1/5 power x to the 10th to the 1/5 power. Well, 243, let's see, 243 is 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, which is 3 to the 5th power. So I've got 3 to the 5th power to the 1/5 power, x to the 10th power to the 1/5 power. So what I did was I took this and rewrote it like that, 3 to the 5th power. Okay. A power raised to a power, you multiply the exponent. So this is 3 to the 5/5 or 3 to the 1 or just 3. This would be x to the 10/5 or x to the 2. So 3x squared. Now, I'm taking an odd root, so it doesn't matter whether the variable is positive or negative, but even so, since it's x squared, it couldn't be negative. Okay. It says evaluate each expression, 27 to the 2/3 power. So the 2 on top means I'm squaring it. The 3 on the bottom means I'm taking the cube root of it. So let's say I've got something like this, a to the m over n power. M is the power and n is the root. Okay. Now, you can do the power and then the root, or the root and then the power, provided that each one of them is real, definable. Okay, so what does that mean? Well, let's go back and take a look at this problem. 27 to the 2/3 power. That's 27 squared to the 1/3 power, or it's 27 to the 1/3 power squared. In other words, I can do the power first and then take the root, or do the root first and then take the power. Well, if I do the top one, 27 squared is some humongous number. Well, let's find it. Let's see, 27 squared is 729. So this would be 729 to the 1/3 power. So then I'd take that to the 1/3 power and I get 9. Okay, let's do it this bottom way. Let's take the cube root, or well, to the 1/3 power first. What's the cube root of 27? That's 3. What's 3 squared? That's 9. I can do this in my head where there's no way I'm going to try that in my head. So if they're both real, it's typically easier to do the root first, tear it down to something smaller before you build it up, instead of making it even larger before you tear it down. Hopefully that makes some sense. Okay. Let's see here. 4/9 to the 3/2 power. Here's a rule I didn't cover earlier. I covered this one. I said if you have a product to a power, you attach the power to each factor. If you have a quotient to a power, you attach the power to both the numerator and the denominator. So this becomes 4 to the 3/2 power over 9 to the 3/2 power. So as I just mentioned in the previous example, I could take the root and then the power, the root and then the power. So I'm taking 3/2 and writing it as 1/2 times 3, pulling it apart. Usually we're going the other direction, but I can pull it apart this way. Okay, 4 to the 1/2 power is 2. 2 cubed is 8. 9 to the 1/2 power is 3. 3 cubed is 27. So 4/9 to the 3/2 power equals 8/27. Now, you could punch this into your calculator, but the answer it would give you would be some long decimal and it wouldn't be an exact answer. So that's why I would do it by hand if I were you. Okay, let's see here. We've got, how about this one? This is a dandy. 1/16 x to the 8th, y to the 4th, all to the 3/4 power. So I have a product and a quotient, in fact, the 1/16 raised to a power. So this is 1 to the 3/4 power over 16 to the 3/4 power, x to the 8th to the 3/4 power, y to the 4th to the 3/4 power. Okay, well, let's take it a piece at a time. Let's take a look at this. 1 to the 3/4 power. Well, 1 cubed is 1, and 1 to the 1/4 power is 1. So this whole thing becomes 1. Okay, let's take this next. 16 to the 3/4 power would be 16 to the 1/4 power cubed. 16 to the 1/4 power is 2, because 2 times 2 is 4, times 2 is 8, is 2 times 2 is 16. So we get 2 cubed, or 8. And this one, x to the 8th to the 3/4 power, power raised to a power, you'd multiply the powers. 8 times 3/4, 24/4, or x to the 6th. And then this one, same thing, power raised to a power, you'd multiply. 4 times 3/4 is 3. So you could write it like that, or you could write it like that. Okay. In fact, you could write it like this too. That's what the book does. Make sure this is in the numerator or kind of straight out from the fraction bar and not down below. Okay, now we're going to go back and forth between radical form and exponential form. Okay, again, recall that the nth root of a is equal to a to the 1 over n power. The index becomes the denominator of the exponent. So let's see. The 7th root of 7p squared q would be 7p squared q all to the 1/7 power. Okay. The square root of x squared plus y squared would be x squared plus y squared, the whole thing to the 1/2 power. Keep in mind there's an implied 2 there. So that index becomes the denominator of the exponent. Let's go the other direction. We've got 6x cubed y to the 1/4 power. This would be the 4th root of 6x cubed y. We've got 7a squared b squared to the 1/3 power. Wait, 1/5 power, my bad. That would be the 5th root of 7a squared b squared. Okay. How are we doing? Okay so far? I guess. All right. Negative exponents. A base raised to a negative power is equal to 1 over the base to a positive power. So cross the line, change the sign. So if you've got x to the -3 power, that's 1 over x cubed. Likewise, if you've got 1 over a to the -n power, that's a to the n power. So if you've got 1 over x to the -4, that's x to the +4. So whether you go down or up, it changes the sign of the exponent in this context. Okay, so now 49 to the -1/2 power would be 1 over 49 to the 1/2 power, which is 1 over, well, what's the square root of 49? 7. Okay. 8 to the negative 1/3 power would be 1 over 8 to the positive 3rd power, which is 1 over the cube root of 8, which is 2. 25 over 49 to the negative 3/2 power would be 49 over 25 to the positive 3/2 power. Again, reciprocal, change the sign of the exponent. But now I have a quotient raised to a power. So I'm going to attach the power to both the numerator and denominator of the quotient. Okay. I'm now going to take the numerator and I'm going to do the root first and then the power. The square root of 49 is 7. 7 cubed, I think. Let's see, I think it's 343. 7 cubed. Yep, 343 over 25 to the 1/2 power cubed, which is 5 cubed, which is 125. If you need me to slow down on any of this, please say so. Anyway, okay so far, I guess. No one's crying wolf, so, or whatever. Let's see, how about this one? Negative 8x cubed over 27 all to the negative 1/3 power. The directions here say simplify each expression. All variables represent positive real numbers. Okay, which means I don't have to worry about absolute value bars. In this problem, since I'm taking a cube root, an odd root, I don't have to worry about absolute value bars anyway. But so what have I got here? I'm going to attach that negative to the numerator. So I'm going to move it and put it there. Same. Oops, come on, here we go. So I've got negative 8. Oh, you know what? Let's do this first. Let's get rid of that negative exponent. So that's going to be 27 over negative 8x cubed to the positive 1/3 power. Okay. So now I've got 27 to the 1/3 power over negative 8 to the 1/3 x cubed to the 1/3 power. Well, 27 to the 1/3 power is 3. Negative 8 to the 1/3 power is negative 2. And x cubed to the 1/3 power would be x to the 3/3 or x to the 1 power or just x. Okay. I'm going to go ahead and rewrite that. I'm going to move that negative sign either to the top or out front. In either case, I don't need absolute value bars for 2 reasons. 1, it's a cube root, and 2, the direction said assume all variables are positive. Okay, let's see here. How are we doing for time? We've got the following: 4 to the 2/5 power times 4 to the 2/5 power. Recall, multiplying powers with the same base, you add the exponents. So this is 4 to the 2/5 plus 2/5, which would be 4 to the 4/5 power. Okay. Again, it says, the directions say, write the answers without negative exponents. All variables represent positive real numbers. They always want us to write exponents positive if we can. How about this one? 5 to the 1/3 power times 5 to the negative 5/3 power. So this would be 5 to the 1/3 plus negative 5/3, okay, which is 5 to the negative 4/3 power, which is 1 over 5 to the positive 4/3 power. Okay with that? How about this one? 2 to the 5/6 power times 2 to the 1/3 power over 2 to the 1/2 power. Well, I'm not going to do anything yet with the denominator. The numerator is going to be 2 to the 5/6 plus 1/3. But now I'm adding two fractions that don't have the same denominator. So let's do that as a separate problem. 5/6 plus 1/3 would be 5/6 plus 2/6 or 7/6. Again, common denominator 6. So I got to multiply by 2/2. So then this becomes 2 to the 7/6 divided by 2 to the 1/2 power. But recall from earlier today, when you're dividing two powers with the same base, you subtract the bottom or the denominator exponent from the numerator exponent. So once again, I've got to deal with a situation. I'm subtracting two fractions. The common denominator is a 6. So I'm going to multiply by 3/3. So this is going to be 4/6 or 2/3. So I'm going to get 2 to the 2/3 power out of all of that. So we're using those rules of exponents, but we're applying them to fractions now instead of just whole numbers or integers. Let's see here. Now we're going to use the distributive property. So I've got y to the 2/5 power times y to the negative 2/5 plus y to the 3/5. I would strongly suggest, if all these rules seem foreign to you, if it's been a long time, that perhaps you go back to section 5.2 and take a look there and kind of review the rules before you attack this section. Because if you don't know the rules, you'll stumble. Okay, so here I'm going to distribute. So this is 5 to the 2/5 times 5 to the negative 2/5 plus 5 to the 2/5 times 5 to the 3/5 power. Okay. Multiplying two powers with the same base. So here we're going to add the exponent. So we get y to the 2/5 plus negative 2/5, which is y to the 0 power, plus y to the 2/5 plus 3/5, which is y to the 5/5 power. Oh, here's another rule. A number or a variable raised to the 0 power is 1, with the exception of 0 to the 0 power. But anything else raised to the 0 power is 1. This is what 5 to the, or 5/5 is 1, or we're just 1 plus y, because something raised to the 1 power, there's like an implied 1 exponent there. Okay, so there's your final answer. Okay, now it says use rational exponents to simplify each radical. All variables represent positive real numbers. What we're going to do, we're going to take a radical expression, we're going to convert it into an exponential expression, then we're going to simplify it, and then we're going to convert it back into a radical expression. Eventually, we'll be able to do this without converting it back and forth. But right now, we're going to do this. So this would be 7 to the 3/6 power, which is 7 to the 1/2 power, which is the square root of 7. So this simplifies into that. Keep in mind there's an implied 1 there and an implied 2 there. All right. How about this one? The 12th root of 13 to the 4th power. So that's 13 to the 4/12 power, which is 13 to the 1/3 power, which is the cube root of 13. Okay, now, how about this one? I've got the 4th root of the square root of x. So that would be, now I can simplify, let's see, we'll start with the outside. So I've got the square root of x to the 1/4 power, right? This becomes that, okay? But then x to the, or the square root of x would be x to the 1/2 power to the 1/4 power. That becomes that. But a power raised to a power, you'd multiply the exponents, and 1/2 times 1/4 would be 1/8. So I've got the 8th root of x. So this simplifies into that. Let's do another one of those. I've got the cube root of the 4th root of 21x. So that would be the 4th root of 21x all to the 1/3 power, which would be 21x to the 1/4 power all to the 1/3 power, which would be 21x to the 1/12 power, which would be the 12th root of 21x. Are we having fun yet? Okay. So again, my advice, go back and review those rules in section 5.2 before you begin. What I find is most questions students have aren't really with the new stuff. It's the old stuff. They're not comfortable with the rules. But anyway, so for tonight, you're going to do section 9.2. I will be back at 1:15 with an office hour today, should you have need of me. I'm going to go ahead and stop the recording.